So today, we're gonna still talk about the rest of DeepAR and do a small code demo. So this is a refresh of what we talked about last time. So first, when we have RNNs, you'll always have some kind of memory vector, and you'll concatenate it with your feature vector from current time step, and do some processing to update your memory vector, as well as to get the prediction for the next time step. So if it's a first layer, or if it's a first layer, then you will be taking the memory vector from last time step and also your feature vector. And if it's any of the following layers, you'll take your memory vector from previous time step from the current layer, and also the memory vector from the current time step, but from the previous layer. And you take those two memory vectors, do some processing. And if this is the last layer, then you apply maybe a linear transformation to the final updated memory vector from last layer to get your predictions for target variables. And we also talk about this vanishing and exploding gradient problem. So one way to deal with this exploding gradient problem is via this LSTM. So it's not important to memorize all the formulas. What's more important is to just know that there's a separate memory vector for the long-term memory and also a different memory vector for the short-term memory. So having this long-term memory vector allows you to kind of keep track of the gradients, have a shortcut for the gradients along the way as you go back in time. And we also talk about DeepAR. This figure is when we do the prediction with a vanilla RNN. What DeepAR does is at each time step, you don't just predict the target variables right away. You actually you try to parameterize the probability distribution and then draw a sample from the distribution as your prediction. So maybe instead of drawing a sample, you can also just take the mean of the distribution as your prediction as well. So a simple example would be a Gaussian distribution, where you will be predicting a mean and the standard deviation at each time step. So it'll be the same as before, where it takes the output memory vector from the RNN, which will be the small h here, and you apply two linear layers, one to get a mu and one to get a sigma. And given the distributions that you parameterize, for example, if we look at the figure on the right, and given the target variable, which we actually observe, you want to maximize the likelihood of observing this ground truth given the distributions that you predicted. So your loss function will try to maximize this likelihood function at the bottom. And this is just a standard likelihood function for a Gaussian distribution. And if you have multiple time steps, you can do some transformation and you'll be optimizing for this function at the bottom. So it'll be actually taking the log of the likelihood at each time step. Okay. And we also went through the introduction for DeepAR. There are several contributions that the paper listed. So the first one is if we use deep learning, we don't need to do a lot of manual feature engineering. A lot of it will be automatically captured by deep learning. And then the second part is what we'll talk about today is how we can draw a confidence interval from the distributions that we parameterize at every time step. And the third contribution is before, if we have a simple RIMA model or those statistical models, for each instance, you will need to train a separate model. But if you're using deep learning, you can just use the instance ID as one of your input features and then train a model based on all the instances. So if you have a new instance, which will probably suffer from a cold start problem because you only have a very limited history for that instance, you'll benefit from sharing the weights across other instances. And the last contribution that I listed is so maybe you don't have to assume Gaussian noise. If your distribution is somewhat skewed, then you can try to parameterize a different distribution. And that will make your loss a lot more stable. And of this DeepAR can be categorized into the encoder and decoder framework. So the encoder will be handling the context range, and the decoder will be for the forecast horizon when we try to make predictions into the future. And this memory vector ideally will be able to summarize what's going on in the context range. And there are some architecture choices that you can make, whether you want to calculate loss just based on the forecast horizon, or maybe you can also incorporate the loss from your context as well. And maybe you can even use the same RNN for both your context and also for your forecast horizon. So the A here will have the same set of weights. Or you can try to use a different RNN in the forecast horizon that's different from what you use in the context range. So you can try all those combinations and see which ones works the best. And then a trick that DeepAR used in their paper is called teacher forcing, which means that which deals with the issue that during training at the beginning, your model will be very off in terms of making those predictions. And if you base on your predictions on, so if you try to predict t+2 and you are basing your prediction on what you predicted for t+1, because we are doing an RNN, so you'll have to use the prediction from previous time step as your input to a next time step. So if your input is already very off and you keep making predictions, your predictions will probably be getting worse and worse over time. So one way to deal with that is during training, you don't actually use your prediction as input in the forecast horizon. You always use the ground truth that's available. It's only during inference where your model is already making some good predictions, then you can base your prediction for next time step using your prediction from previous time step. And let's take a closer look into this cold start problem. So in addition to just having to share the weights across all the instances, they also add this concept of cold start into their training. So during training, maybe we can just spend some time reading this paragraph. Okay. So what this paragraph says is that during training, your first window that you sample, so recall that we always supply rolling windows to gather to cut the data set into rolling windows. And then what this paragraph says is that your first window doesn't necessarily have to contain all the ground truths. Maybe for example, if your context range is 100 time steps, you don't need the entire 100 time steps of ground truths. You can maybe just have 70 steps as ground truths, and then the first 30 steps will be all padded with zeros. So this will help at inference time if we have a co-star item that only have 70 steps of history instead of the whole 100 steps. Okay, and the next concept that we'll talk about is how to generate those confidence intervals using a technique called ancestral sampling. So right here, the code is only coming from the decoder part. We assume that we already went through the encoder, which gave us this hidden and cell, which correspond to the two memory vectors from our LSTM. So let me actually first draw a picture. So if we already have this context range, and we end up having those two memory vectors. So this is our short-term memory vector H, and also a long-term memory vector C. And we want to predict into the future. What we do is that, so this is our context. What we do is that we'll first use a C to parameterize the Gaussian distribution. So we'll be outputting a mu as well as a sigma for a first time step in the forecast horizon. So mu naught and sigma naught. And then based on this distribution, so there's a distribution, and we take one sample. And then based on the sample, we assume that's the ground truth and then feed into the next time step. So we take the sample and feed into the next time step, and we get the mu 1, sigma 1. And we get this distribution again, which we take another sample. And we keep doing that. So this is called one sample pass. So we're maybe doing this for 30 times. So we get one pass. So maybe one of the paths look like this. And we go back. So we want the idea of having this confidence interval is we go back to the first time step in the forecast horizon and then resample another different sample from this H and C, which we got from the encoder. So we try to generate a different sample. Maybe we call it mu hat and sigma hat. Sorry, mu prime and sigma prime. And then this way we can draw another sample path. So maybe it looks like this. And at the end, we can draw like 100 of those sample paths. And the way we get this confidence interval at the end is for every time step. So every time step, we will have, if we take 100 samples, then at every time step, we'll get 100 samples. And based on those 100 samples, we can calculate maybe a mean and a standard deviation or maybe some quantile values. So this will serve as our confidence intervals that we predict. Yeah. And the code here does basically this thing. So the first for loop will be the number of times that we want to sample. And next, inside the for loop, we'll go through the prediction number of steps, predict steps to get our first sample, and then draw many samples this way. And then at the end, maybe we can take the median for every time step. This will serve as our final prediction. And then the last thing, I think this is the last part I want to talk about is this evaluation metrics. So in addition to the MAE, mean absolute value, or mean absolute error, or MSE, mean square error, the paper also have this ND and RNMSE. So this is pretty much just very similar to MAE and MSE. The difference is that it normalizes the MSE and MAE based on the ground truth. So the ND will correspond to the L1 error, and the RMSE will correspond to the L2 error. Another metric that they use to evaluate the confidence interval is called this quantile loss. So the row quantile loss here, the basic idea is that if you predict something that's bigger than your ground truth, then you'll penalize it based on which quantile you are predicting. So if you are predicting the 90% quantile where rho equal to 0.9, that means you want your prediction to be greater than the ground truth for 90% of the time. So in that case, if what you predict is end up being smaller than the ground truth, then we'll penalize it by a very large penalty. So we'll be having this 0.9 times the difference in your prediction. Versus if you predict something that's smaller than the ground truth, then you only penalize it by a small amount, which is 1 minus 0.9, which equals to 0.1. So only penalize 0.1 times the difference in your prediction. And instead of doing this ancestral sampling that we talk about here, in some following papers, they actually just directly train the model based on this quantile loss. So you'll be directly predicting the 90% quantile, the 10% quantile. So you don't have to do this ancestral sampling because this sampling is very expensive to do at inference time because you will need to draw many samples and then take the median. It will be better if you can just directly predict the quantiles. And this is what I have for the first part. Then we can talk about let's first talk about so I wrote some GitHub instructions. I guess this is probably quite familiar for a lot of you guys. So I'll skip this part and maybe you can read this part at your free time. So you'll need to generate the SSH key or using personal access tokens to be able to sync your GitHub account onto your device. And then there's also some instructions on how to sync your code from your own local laptop onto the server. So this part is very straightforward and will be very boring for me to read this over. So you can read through this at your own pace. So all of those documents can be found in this Google Drive. And then the other part is this Colab, which does the data processing for the M5 dataset. So this is a dataset I was talking about that we'll be using as a proof of concept to implement the two baselines, one for LSTM, which will be based on this DeepAR that we just talked about. And I think in 1 or 2 weeks, we'll be talking about transformers. So you'll be running those baselines using this M5 dataset. So you can try to run the blocks in this Colab. And there's actually a small issue that I ran into. So because I wrote this data preprocessing pipeline 2 years ago, I think there was a upgrade in pandas. So some of the functions they probably changed, and I ended up having a lot of negative ones. So maybe you can try to debug this code and see how to get rid of these negative ones. And you can try to do some very basic EDA on this data set just to get familiar with the different variables and what they mean. So actually, if you Google this M5 competition, they have a big PDF that you can read over. I will also put the PDF in this Google Drive. But don't spend too much time on just this one data set.